processes are assigned in such a way to minimize the wasted memory within partition. And what is this wastage called? Yes, what do we name this wastage as? It is known as internal fragmentation, right? Because it is within the partition. That's correct. Okay. Now, if you want to go with placement algorithm for unequal size, we have two approaches. Right? Let us look at the figure first. That will make you understand better. Fine. Look at the left side model where we are having waiting queue for each partition. We are having single waiting queue for each partition. And on the right hand side, you are having just a single queue. Right? So if you analyze the left hand side, right, what is the benefit of that? If you are having separate queues, you can achieve what? One queue per partition. That is the first method, right? Isolation, yes, good. Any other point? Please mention in that in the chat. What is your observation of the first model? More processes can be fit. Okay, we can say that. Anyone else would like to answer? What is the benefit? No starvation. Okay. The negative aspect you can easily see because you need more space, right? You have to maintain multiple queues. They have to be allocated memory. They have to be searched. So overhead is there, agreed. But over here we have an advantage, right? Let us look into this. If you go with one queue per partition, right? It is optimum for a partition point of view. Yes or no? It is optimum for a partition point of view. Because if you are having a request of 2 MB and if you are having a request of 1 MB, where both the processes will go in this case? 2 MB process will go into 2 MB queue. Yes. And 1 MB process will also go in the first partition queue. Okay. So the amount of wastage will be less. Because what will happen? If this queuing model was not there, then where the 1 MB will be loaded next? It will be loaded into 4 MB, right? So the fragmentation amount will be more, right? But that 1 MB process has to wait on the other side, isn't it? Are you getting the comparison, right? On either side of the things, right? I'll repeat once again. If you are going with single queue per partition model, and if your request is in this order, 2 MB and 1 MB, right? So 2 MB can be accommodated in the first partition, but 1 MB process will have to wait. Agreed? 1 MB process has to wait, right? But if you go with single queue for all partitions, can we overcome this disadvantage? Can we go with single queue for all partitions? Can we overcome this waiting period? I hope you are getting my question. Right? Okay. Yes, it can be starving out, or you can say fragmentation will be more, isn't it, Urjit? Because I'll be allocating that 1 MB into 4 MB partition. So amount of fragmentation will be high. Okay. So it is again a two-sided coin. I hope you are getting this, right? Starvation won't occur over here. Starvation won't occur, right, Urjit? I hope you are clear with that. Because see, you are going to load that process anyhow. So starvation is not going to be in the picture when we are having one queue for all partitions. But when starvation can occur? Can you tell me when starvation can occur? Let us say your requests are like this, for example, 1, 1.5, right, 2, 1.75, right? If you are having this kind of execution and single queue per partition, are you going to starve out the 3 processes for at least some time? I hope you are getting my point, right? Yes. Okay, so think in both the ways, right? That's what is important over here. Okay. Let us go through it once again. If you go with 1 queue per partition, it is optimum for partition point of view, but it is not optimum from system point of view. Why? Because the amount of fragmentation will be high or will be less in this case. Or in other words, starvation will be more. Starvation will be more. That is one thing, right? Okay. If there are no processes which can fit a particular partition, it will remain unused. This is a very, very important disadvantage. Why? Because if you continuously keep on receiving requests less than 4 MB, what will happen in that case? Think about this model. All the requests are less than 4 MB. Then which queues will be filled? Which queue will be full in that situation? 2 and 4. Both the queues will be having lots of processes waiting. All other partitions are free, but can you load a process into that? This is an important point to understand, right? Remaining partitions are free, but you can't load it. Why? Because the algorithm says that you can't load a partition or you can't load a process, right, over there. Right? Exactly. So that is not a good solution. So after some time, what OS has to do? It has to track the queue, right? And look at the queue length. If the queue length is very high, what it should do? Take out some process from that queue and place that in the remaining partitions. Then only you can execute efficiently. Otherwise, the efficiency will degrade. Okay? Understood this problem, all of you? Right? This is an important thing, right? So the summary is which method is suitable. Although you might have internal fragmentation, still, which method we should go with? Single queue for all partition or single queue for entire memory. That's what we say, right? Are you clear with this? This is the correct model to use, right? Okay, in single queue for all partition, if the entire queue is searched, it is always selecting the largest process which can fit. Then there can be starvation in single queue for all partition. So that is the worst case, actually, Urjit, right? But we are having better advantages, right? So that's why we would say that this is comparatively better approach. I hope you agree to that, right? Yeah, sure. So what he is saying is in single queue, if all partitions, if the entire queue is searched, then it always selects the largest process. Okay. So what he is saying is sometimes what happens is you are getting similar types of requests. And what is your criteria over here? You have to fit into whatever is the next available, right? Suppose you are having number of requests of similar size, right? Then you might have to make the other processes wait for some time, right? If your queue length is very huge, that is the point he is trying to make, right? Then yes, you might have to wait, but that waiting time won't be too much, right? Unless your system hangs. If your system hangs, main memory will remain occupied. So the processes which are lying in the queue will be starved out, right? So that is possible there, but that is the worst case, as I said, right? Ideally, what happens is a process executes, it goes out, right? We have the space available and we are happy. Right? That's how we work, right? Ideally. But in worst case, it is possible, right? But the amount of starvation is very minimum, right? If the system holds correctly, right? Yes, right? Okay. So are you clear with these two models and comparison, all of you? Hope you are finding this interesting as well, right? We are comparing different approaches, right? And there can be many logical questions based on this, right? Even in MCQs, there can be many logical questions, right? So you should be ready for that, right? Okay. Fine. Advantages of fixed partitioning, right? Now, after seeing all the methods, you must have observed that the methods of fixed partitioning are very simple, isn't it? Because what we are deciding, either we say that we'll go with fixed partitioning of, let us say, 8 MB, or we will go in multiples of 2, or in addition of 2, right? In any case, the algorithm is very simple. We are saying that everything is fixed. Okay, so that's why they are relatively simple. And the important thing is it requires minimum OS and processing overhead. Why so? Because we don't have to check the available process size, right? Because if you are going with dynamic partitioning, first you should know how much space that process is requiring. Then look at your available space, search where is the available space present. Are you getting? There is a lot of overhead involved in this entire task, right? While over here, it is very simple, right? Even I think you can write the program for this, right? Can you write a simple program for this loading, right? Even with multiple queues and single queue. It's a simple approach, right? You can write a simple algorithm or simple program for this, right? Okay. And the further advantage is, in case of unequal size partitioning, we have flexibility. Why? Because we have multiple options to choose from. You have different sizes available, and you can optimize according to your current requirement. Okay. So equal size partitioning is restrictive, while this is flexible, unequal size partitioning. Is the difference clear? Equal size versus unequal size. And where both the methods belong? Fixed partitioning. See, we are going to see many methods. So I hope you don't mix it up, right? Okay. Now, the problems, right? We have already seen, but let us look at from efficiency perspective. There are two more problems. Number of active processes is limited by the system. Why so? For example, I gave you that situation. We are having 100 MB of space, and we are dividing that into each partition of 10 MB. So how many processes I can load at maximum? Only 10, right? This is actually a very critical drawback, right? Because if you are fixing that only 10 processes can be loaded, right? And what if all 10 are IO bound processes? What will happen in that case? Ideal CPU, isn't it? Because those processes will execute for some time and they will be suspended waiting for IO, right? So when we go with fixed partition, right, we are going to limit number of active processes, right? Active process means what? Can you compare that with the state? Number of ready processes, right? We can say that, yes, right? Exactly. Fine. The other disadvantage is, understand this statement carefully, a large number of very small processes will not use the space efficiently. I already have given you the example of this. What was the example? If you have a continuous supply of very small processes, what will happen? Yes, exactly. A lot of internal fragmentation, right? A lot of internal fragmentation plus a lot of wastage, right? So if you take example of either a fixed partition or a variable length partition, this is a common problem. I hope you agree. Yes or no? Wastage is a common problem, right? No matter what is your allocation method. Okay. This is the reason, this is the basic reason by which we have to move to dynamic partition. Got it? We have completely analyzed, right, this method in detail. So let us now introduce this at least before we end. Partitions are of variable length and number. That means what? The size of partitions is not fixed, as well as number of partitions is not fixed. Why? Because we will go on merit. We will go on request basis. Okay. So a process is allocated exactly as much as memory required. No more, no less. Right? What about internal fragmentation in this case? Internal fragmentation is minimum. Yes. Ideally, it will be 0. Ideally. There are some exceptional cases. We will see that, right? Okay. Let us take an example, right? Suppose you are having 8 MB of a space occupied by the OS, right? Remaining 56 MB is available, okay? Process P1 comes with 20 MB. Can we accommodate that? Yes, right? So we will allocate that and we are left with 36, okay? P2 comes with 14. Still, it can be accommodated. Remaining is 22. Are you following this up to this, right? A, B, C. Okay, fine. P3 18 MB. Just observe this, right? We are actually creating a problem over here. I'll just take 1 more minute, right? And we'll finish. The last part where P3 is loaded, now you are left with 4 MB of space, right? In this position, there is no ready process. That means P1, P2, and P3 all are in block state, right? So suppose your OS decides or dispatcher decides to swap out P2. So now I'll create a hole of 14 MB. Yes or no? We are creating a hole of 14 MB where the process can be loaded. Okay. What will happen if this kind of swap in, swap out continues for some time? Can you imagine what will happen? You will be having very small amount of space left where no process can be loaded, right? Suppose like this. See, we are continuing, right? P4 is loaded over here. You can see that over here, right? In this space. Now, again, no process is ready. So P2 is in ready suspended state, fine. But the size of P2 is large. What was the size of P2? 14 MB, right? So I need to swap out P1 for that. I am swapping out P1, creating a hole over here, right? P2 is loaded. See what is happening, right? One hole over here, one hole over here, and the other hole over here. This is a fragmentation. But which kind of fragmentation? It is outside partition. It is outside partition, and this is known as external fragmentation. Clear? Right? Go through this example once again, although I've gone through it quickly. If you don't understand anything, we'll discuss it tomorrow once again, right? Okay, that is why in today's device, they provide inbuilt yes, exactly. So defragmentation is frequently done, right? Just to combine the holes together. Because if you combine the holes together, right, you will get a large space. Yes, definitely. So that is why defragmentation is a very important thing that has to be done frequently. Right? In earlier days, the people used to do it manually, but nowadays OS is trying to do it automatically. Right? So this is the reason for which defragmentation is required. Okay. Therefore, file. Okay, Rishi, there is a question for you. This defragmentation is a solution for this, Preet. That is correct. Right? That is one of the solutions. And that is known as compaction. In OS, we will see that in tomorrow's class. But the method is known as compaction. Compaction means bring the holes together. We don't call it defragmentation. We call it compaction. Right? Okay, so let us end it for today. We'll continue tomorrow. Okay, thank you.